Yeah, yeah. Oh, no. Yeah, I think we met briefly before. Yeah, and also he was in San Francisco. A CodeCon thing. Okay. Oh, okay. Cool. Yeah. Yeah, yeah. Okay. Oh, okay. All right. Start. Um, this is. Oh, first of all, did people get drinks? Everybody got the memo about the drinks, about the bar and stuff. You didn't get a drink. Okay, I'll bring you back a drink in a minute. What do you want to drink? What do you want to drink? A beer or Corona? Okay, great. So, yeah, Dan will be starting in just a minute here. He's working on some pretty cool stuff with FPGAs, and I don't know. He'll explain a lot of that. We've been working a little bit on FPGA stuff. Gave a talk at Black Hat, and let's see. Dan has lots of experience with messing around with that sort of thing, and that's my intro. So here's Dan Moniz.
Thanks. Everybody hear me? Yeah? Good. All right, so this is the Cheap Crac presentation. I'm Dan. Hi, everybody. Thank you for coming to Toorcon. So, I mean, I've already got done with the who, but basically the rest of the presentation is going to go in this format. Who, you've already been there. Why, and then how. And then really the most of it is taken up by how. There's about 20 slides. I'm already ashamed about how many bullet points there are. I really don't like to do bullet point heavy slides. I criticize all my friends at cons for writing slides with tons and tons of bullet points. But I commit the same crime here. Having said that, a lot of what I'm going to have to use the other mic here. I have to move around. Can you hear me? Undo this one? Oh, all right. A lot of what I have to say is more about, I mean, there's points on the slides, but a lot of what I have to say is more about the historical context of the project. And really, it's less about, you know, for people who's heard of Cheap Crac or has heard of Deep Crac, which is obviously the play on the name. Okay, who might have saw the Black Hat presentation, either in person or, all right, one or a couple people. So most of this stuff will be new. We'll figure it out as it goes along here. So what were the beginnings of the project? The project is called Cheap Crac. For people who haven't seen it, I know that the reprint in the program for Toorcon is essentially the same thing I said in the CFP. What Cheap Crac is, or tends to be, originally anyway, was a desk cracking project, and it still is. It began as sort of a random thought experiment. It was a couple of people on a mailing list at the end of last year sitting around saying, well, you know, we're thinking about trying to crack crypto. A couple of people were working on cracking things like WPA, including Hikari. And we were trying to figure out, well, you know, it would be neat if we could build some kind of generalized platform for this. And to be honest, that's already built. I mean, Hikari and Pico Computing, the company he works for, have already really built a very generalized platform. It's essentially a 4U box that has 16 PCI card slots in it. And each PCI card is just a bus for a PCMCI card bus card. And they make card bus cards that just basically are really fast Xilinx FPGAs with a bunch of, you know, memory and I/O and stuff on them. And those things can be reprogrammed as hardware. I mean, reprogrammed in terms of you can create another hardware design and put it on each individual FPGA and each card and run them really fast in parallel. So for any problem that is parallelizable, like crypto, of course, but also like things like bioinformatics, algorithms, and etc., you can do it quickly. But it costs a lot of money. It's not a lot of money. It's, you know, $40,000 or so, but it's a lot of money to people in the room who maybe want to try to do this. Thank you. Yeah, Mancala hour. So what we were thinking about doing was, well, okay, let's really try to go the opposite end of that spectrum. If we accept for granted that $40,000 of really cool Pico computing hardware is badass, but still more expensive than I have out of my pocket now to spend on, you know, essentially just playing around with stuff. What can we do on the extreme low end of that, right? What can we do that's like extremely cheap and is also easy to procure, easy to learn about, is kind of developed with the intention that people are going to mess with it to learn about things. FPGAs in general were already something I was playing with. I had bought a little dev board and had been, you know, messing around with it and trying to get it to do things. And I had been looking into FPGAs mostly by reading about them and by reading about hardware design languages for a while. So I was really interested in finding out, how do I actually build something useful out of this? And out of the discussion, the mailing list said, well, okay, let's just say we want to build a desk cracker. Let's just build that, because we know desk is weak. We know that a desk cracker has already been built. The EFF did it back in 1998, and all of that code and all of those project details are publicly available. So who's seen this book before? All right. A few people, but far too few. Go buy this book. You don't have to buy it. It's scanned, and it's available on numerous websites, including Crypto.me and a bunch of other ones. But I highly recommend going and buying it. I don't think it's had a new edition. It's published in 1997. They actually published the book before they finished building the machine. It is all free source content, so you can go and find it online, but I highly recommend buying it anyway. I don't know if the money still goes to EFF or if O'Reilly is pocketing it at this stage, but it doesn't matter. It's a book worth buying and having on your shelf. It came in handy for me because literally I took it off the shelf, flipped to pages of OCR-able source code for all the VHDL, and then basically started implementing. This is one example. This is the chip, essentially, that book defines. The book defines a bunch of other things, too. It defines the actual hardware machine and the board this chip is sitting on, but this is the actual chip, the AWT 4500 Deep Crack chip. AWT stands for Advanced Wireless Technologies, which was the company that EFF, John Gilmore, and Cryptography Research, which were all the partners in the project, partnered with to actually fabricate the chips. AWT was a company that fabricated ASICs for small runs. And in this case, the run was like under 2,000 chips. So again, in the context of this thing, I'm not trying to say this is something new. Implementing crypto in FPGAs is a common college course kind of project. It doesn't mean it isn't important or isn't useful. It just means that I'm not trying to say, this is world-shaking kind of stuff. It's also not terribly practical. If you really wanted to crack crypto, even spending as little money as $40,000 on a Pico computing box is, perhaps not even practical. Not because it's not good, but because if you are serious, quote unquote, about it, you can just, fabricate your own ASICs just like EFF did, but in a secret fabrication facility with people who will never ever leak your IP and who will provide you a chip and a machine that will do it in something like hours or minutes, as opposed to essentially what we'll see as days. I have the $250,000 here figure, which will become sort of self-explanatory in a minute. But really, the whole goal of the project was about self-exploration and community. How can we build a grassroots project that has some kind of target to it? It's not just open-ended. We want to crack desks in a certain amount of time. And we can bootstrap off of all this community knowledge, which is the stuff that EFF did, and also get FPGAs in the hands of people, right? This is sort of a lot of what open source does in the software world, right? Somebody finds a project that is aspiring to scratch an itch they have, and they can contribute to it. And then they, use that, and they proselytize it, and they show it to other people, and it goes from there. This is much the same thing. The problem is that up until fairly recently, say in the last 5 years, give or take, FPGAs have not been powerful enough or cheap enough or dense enough to really be people are going to go out of their way to buy just to play with, just to tinker with, right? You really had to have kind of specific uses in mind, even if those uses were reconfigurable uses, even if you knew you were going to do something with it later. You really had to be into digital design or logic or something like that. Now that's not the case, and this gives a project, who in the room would be interested in cracking desks just for fun? Right, obviously a few people would be here if that weren't the case, right? So that's the kind of thing that can kind of appeal to people, and the difference is with you can go to SourceForge, you can download something, you can play with it, you can get a compiler, GCC for free, and you can go. With FPGAs and with any kind of hardware, you need to have something physical, right? So that was another constraint, was to make sure that whatever we wanted to use wasn't exorbitantly, expensive to acquire. But a little background about Deep Crack. Built in 1998. The book was published in 97. I think it actually came out in 98, but it was finished writing in 97. The actual machine was built in 1998, and it cost, at the time, $110,000. They budgeted for around $250,000. But that's in 1998 dollars. So today, that's with inflation about $243,000, and the budget, if you assume the same budget, would be about $289,000. But let's just round up and call it $250,000 and $300,000 each, right? What does that get you? It gets you 1,536 desk cracking application-specific integrated circuits, or ASICs. When I say ASIC, and when in the industry says ASIC, think about is chips, right? Essentially, an application-specific integrated circuit is a chip built to do a specific thing. In this case, it's Crac-00.avi. They built a machine which took 64 of these chips per board, and they had 12 boards per chassis, and they had 2 chassis, so 24 total boards, each with 64 chips, 1536 chips. And they put them in essentially recycled Sun 4 470 chassis that ran on VME bus. They just used it as industry standard. It was easy for them to cheaply build a board of their own design that would take 64 of these chips and have all the electrics basically work. They could just plug it in and slide it into a machine and have it go. So this is one of the 12 boards per chassis. So you can sort of see how it's laid out. And then the VME connector on the far end. Right. Each chip in Deep Crac is called search units, 24 search units. And a search unit, if you look at the specification, a search unit is, it's not exactly a full desk core. It doesn't really need to be. It implements most of it. But essentially, each search unit alone cracked 2.5 million keys per second in 98, right? And that was pretty nice for 98. It's pretty nice now, really. But again, it's application specific, meaning this hardware is not reconfigurable, right? It's built, it does exactly what it does, and that's it. All it does is Crac-00.avi. Each chip, by virtue of having 24 of the units, cracked 60 million keys a second, and they had 1,536 of them working on a problem that is inherently parallel, right? A lot of times you'll hear people refer to problems as embarrassingly parallel, and crypto is one of those problems, right? A DES is a pipeline. It looks exactly like a pipeline. And so it's easy. There's no data dependency. You can easily put as many of these as you want and scale linearly to get less time, right? You have to run into issues about power and cooling and all those things. But essentially, it doesn't cost you anything to just add another one. You just reduce your time by that much. So essentially, the entire Deep Crac system, both chassis, full of chips, running full bore, assuming no hardware faults. They had some chips built in for redundancy in case one chip decided to short circuit or blow up or whatever, would crack 9.616 e to the 10 keys per second. Roughly, what's that, 92 billion keys a second or so, right? And so that gives you an exhaustive total key space search time of DES. In average, the mean was about 4.5 days. Right, so they estimated they could search all of DES key space in about 4.5 days. Now they used this machine on a DES challenge, RSA DES challenge. I think it was DES challenge 2, and they think they got the answer in just under or just below, over 2 days to one of the to the key in question. 1998 was so 8 years ago, though. I mean, don't get me wrong. I mean, it's impressive even today for the kind of effort it was, mostly because a small, underfunded, civil rights organization decided to take it upon themselves to build something that the government said was impossible, right?